Let's come back to today's lecture. So today I want to give one more lecture, final one on this dimension argument. Then from Thursday, we'll move on to a new topic. So let's recall last time we talked about dimension argument where we want to bound a family of discrete objects. And the idea is to map it, so dimension argument, yeah, the idea is we map it to some vector space such that this is into injective, and the image is linearly independent. And from this, then we can get that the size of F is the same as its image will be at most the dimension because of the independence of the vector space. We saw several examples, and one such nice typical example is a classical example, Frankel-Wilson. So let me remind you what is Frankel-Wilson, and we will see some nice application of it. So we have a P is a prime. So P is a prime. I am, yes, P is a prime. And then we have F, which is a family of subsets of N. If we satisfy two conditions, one is that the size of every set in our family has cardinality a multiple of P. So that means 0 mod P. Second condition is every pair of intersection, distinct ones in our family, their intersection size is not divisible by P. It's not a multiple of P. If we have these two conditions, then the conclusion is that we can bound the cardinality of this family fairly well by the sum of binomial coefficients of the first P layers. So for particular choice of N and P, this sum is exponentially small than 2 to the N. So it gives a very strong bounds when we're just forbidding a single, in some cases, a single intersection size. The application we want to see today is a geometric one about sets with no orthogonal pairs. Okay. Basically, we want to know these sets, they are very small. It turns out to be exponentially small. Okay, let's make things precise. So the thing we cared about is, this is the statement. Let me directly write the statement. We have P, which is a prime. And N equals to, so N equals to 4P. And we have a set of vectors, let's call it V, which is unit vectors. A set of unit vectors in nth dimension. If we require that V does not contain a pair that are orthogonal, how large can it be? If no pairs in V are orthogonal, then the measure mu v is exponentially small, exponential in n, of course. Here, by measure, I just mean let's look at the spherical surface measure and then normalize it to 1. Let's consider normalized spherical measure. Because to be precise, this is in the unit sphere, right? Normalized spherical measure, which is rotational invariance. Okay. So how can we possibly prove that if we normalize the measure of the sphere to 1, then if you take any subset of vectors with no orthogonal pair, yeah, if you want to draw a picture, this is your sphere, we take some part of it such that no two are orthogonal, then such set must be exponentially small, like e to the negative cn, right? That's our goal. Idea is the following. We have sort of hinted you we're going to use Frankel-Wilson, all right? And we know for some particular choice of n and p, actually this pair of choice of n and p, this bound is exponentially small than 2 to the n. So we have some exponentially small sets. This satisfies if you forbid a single intersection size, you could get exponentially small size sets. So if somehow we can correspond this set of vectors so that we can somehow construct some sets which is like a observation group to compare to V, such that orthogonal pairs in this observation group correspond to these forbidden size sets. Okay, so let me write it down, the idea. We're gonna discretize the problem. Using a random observation group for comparison. And this will be the rho V, rho L below in the proof. We will see what is this guy. Such that and orthogonal pairs correspond to pairs with forbidden intersection size. Okay. So how are we going to choose this clever observation group in which the pairs of vectors, observation group of vectors, such that pairs of vectors correspond to forbidden intersection size? So here's the choice, the smart choice. We're going to take I'll just write proof. Let f to be all the half sets of the first integers. So remember, our n is 4p. So we choose all the half sets. And then we're gonna, so if you have half of them are 1, half of them 0. Think about this set correspond to 0, 1 vector. Now, what we want to do is we look at the characteristic vectors of these half sets, but we want to normalize it so they live on this unit sphere. So let's look at the normalized version. But also, we want to somehow centralize it. So what we would do is we would, so that it sum up to 0. So you're going to shift it, consider, write alpha to be 1 over square root n, and then associate each set f in our this family a unit vector. Let's call it VF. And what's VF? Basically, whenever this one are in F, this one not in F, right? Let me show you. This is in F. This is not in F. Let me write FC. So in F, we're going to change it to alpha. Not in F, we're going to change it to negative alpha. Because each alpha is 1 over square root n. So the L2 norm, the length of this vector is exactly 1. So this is a unit vector. Write it out precisely. That equals to indicator characteristic vector of f, but we then have to make the complement negative. So minus the characteristic vector of the complements. So let me write more precisely of the complements, and we make it a unit vector by multiplying by alpha. Now we have our observation group, and then set L to be all the vectors obtained in this way. Okay, so looks a little bit mysterious at the moment, but let's see what's the nice property about the vectors in this set. So for any two sets, Fg in our family, this half set family, let's consider their corresponding vector in L. C their inner product when they are orthogonal to each other, right? We can see that if you take the inner product, this equals to what? We have to multiply this with VF. So it equals to, let me write it down first. Take out the scalar, we have square of them, times okay. Let's explain why is this true. So suppose we have, since we take out alpha square, so we just need to look at 1, negative 1 vectors. If you have f is 1, 1, 1, 1, 1, and negative 1 like this, so this is your f, and you have g that looks like this. Here it's 1, the rest is negative 1, right? So when you take the inner product, when do you get positive? You get positive when we in the intersection. That's why we get a +1 here. We get positive if you all become -1, which is precisely the complement of the union of them. Also here. So this is n minus f union g. And all the remaining ones, which is in the symmetric difference of f and g, we get opposite signs as a -1. Now let's simplify this expression. This equals to, so alpha squared becomes 1 over n. This is easy to compute. Not hard to see that this is m minus 2 times the symmetric difference of f and g. Okay, simplify further, that's 1 minus 2 over n is 1 over 2p. So f g over 2p. This is what we get. Vf Vg equal to this guy. Okay, now we will see why we choose this set L. The nice thing about it is that Vf, Vg orthogonal to each other, meaning that their inner product is 0, if and only if this guy is 1, right? That means this is 2p. Let's write it slowly. If and only if symmetric difference is 2p, but each one of them is 2p size. We have ground set n, each one choose half of them. So it's a 2p uniform family. This is 2p, this is 2p. To have their symmetric difference to be 2p, they have to overlap at exactly p elements. So this is the same as f intercept g is p. Okay, good. So we achieved what we wanted to do. Part of it is that we found some discrete sets, which is precisely this one, and associated, we find this discrete set of vectors such that two vectors in this discrete set are orthogonal if and only if they have this particular intersection size. Very good. So what does that mean? That means now we can look at, let's take L as a observation group and look at V, our set with no orthogonal pair, how we intersect with L. All right? Because of this, vectors in here, pairs are orthogonal if and only if they have intersection size P. But also vectors in here are never orthogonal. Okay, and hypothesis, no pair in V orthogonal, then by Frankel-Wilson, we have, this is at most the sum of ni, I goes from 0 to p minus 1, which is exponentially small than 2 to the n. Let me just write as 1 minus c times n, exponentially small. Any questions so far? All right. Now the rest follows quite quickly. What we're going to do now is this set has no orthogonal pair. This property is maintained if we apply a random rotation rho to it. So we're going to make L random. Okay. Now we do averaging. Take a uniform random rotation rho. Okay. Then V intersect rho L, this new rotated random set L, still satisfy that. For this is still true for every outcome. That's on one hand. On the other hand, if you look at the expected size of this guy, expected size over this uniform random rotation rho, what do we know? Well, this is basically the sum of a point P in rho L, if you want to write it, the probability that this point lies in the set V, right? But look, a point which was initially in L, after a uniform random rotation, this point is basically uniformly distributed. This point P is all points in rho L is uniformly distributed over the sphere. What does that mean? That means a uniform random points lie on our particular set of vectors V equals to just the measure of this set. Times the size of the set L. Okay. Now we are done. In expectation, the intersection of V with respect to with our random observation group is equal to this. But for every outcome of rho rotation, they are exponentially small. So we have, combining these two, we have mu V times L is at most. So what is L? We know what is L. L is 2n choose, n choose n half, right? L equals to the size of F, which is at most 2 to the 1 minus Cn. But this is not exponentially small. It's like 2 to the n over square root n, remember? So we have mu V exponentially small as desired. We've seen this way of upper bounding a quantity through a random observation group before. Remember in Katona's proof of circular method, let me write it again. Just to remind you, this is a nice way of proving upper bounds, a random way to do averaging, is we have random averaging. Remember, we have some target group A, and we have some control group B. Usually B is random. Okay, we introduce this smart way of introducing some random group, and our goal is to upper bound size of A. In this case, we want to upper bound the size of V. But it's a continuous, it could be a continuous set, so look at the measure. And remember the property I mentioned before. The property is that in this random control group, every element B in B must be uniformly distributed, uniform over the ground sets. which is the case here. We have this P in row L is uniformly distributed over the ground set, which is the unit sphere. This then implies the probability that this every element in B lies in our target group equals to the measure of A, which is size of A basically. This is what's going on here. But on the other hand, this implies expectation of A intercept B is equals to size of B times mu A. This in our proof here is this step, right? Mu V. So we can bound things in expectation associated with the measure of the set we want to upper bound. On the other hand, if we choose this B control groups in a smart way, for every outcome of this B, for every rotation row, the intersection is small. Okay. Then we can finish the proof. Just want to remind you this random averaging argument. Okay. So the next application, a very important one, is about Borsuk's conjecture. Jeff Kahn and Hugh Carlyle disproved in the early 90s an old conjecture of Borsuk. So Borsuk in 1933 conjectured the following, that if you have every bounded set in Rn, think of it like a ball, can be decomposed or can be covered into at most n+1 sets of smaller diameter. Okay. So after this conjecture is posed, over the course of, I don't know, half century, before early 90s, or half 50 years, some special cases are proved to be true for Borsuk's conjecture. Some nice shapes like these balls or boxes, these nice shapes. But in early 90s, Kahn and Carlyle found a very short proof, surprisingly, disproving Borsuk's conjecture. Not only that we cannot use sets of smaller diameter, we cannot use n+1 many to cover the original set. In fact, linearly many or polynomially many, even exponentially many, is not enough. So they found a set for which, if you want to cover it by smaller diameter sets, you need exponentially many. So Kahn and Carlyle, this is 1993, disprove it in a strong sense, if we want to cut a set into pieces with smaller diameter,
There is a problem in the chat. What does the composed mean?
okay, 1 second.
What does
Decompose just means, so if you have a set, you want to cut it into small pieces so that no point is left uncovered. You want to cover a set by sets of smaller diameter. That's all it means, decompose. So if you have a set S, you want it to be contained in union of, let's say, Ti, where Ti diameter is smaller, strictly smaller than diameter of S. And we want to use as fewer pieces of Ti, smaller diameter sets, as possible. Any other question? How do I see chat here? Okay, I cannot see on the laptop, on the iPad. So how do we prove this thing? Well, let me first write a statement of their theorem, and then let's see how we prove it. So maybe write it as a theorem. Concali. P is a prime. N equal to 4p. Then there exists a set X in some space. Let me not review it for now. Of size n choose n over 2, such that every subset of X with smaller diameter has size and most the sum of the first peak binomial coefficients. All right. Well, first of all, this immediately disproves Borsuk's conjecture, because for this set X, if you want to cover it by subset of it with small diameter, every such subset of small diameter is exponentially smaller than X itself. So that means you need to use exponentially many of its subset to cover it. The idea is okay. We want to construct the set which is the set X here, where the orthogonal pairs So we've seen already, the hint is that we've seen in this proof that we can construct a set of vectors, unit vectors, of size n choose n over 2. So that's the right size we want. And we can write down when exactly they are orthogonal, right? They are orthogonal exactly when their intersection is P. But if here we can somehow show that the orthogonal pairs are the ones that realize the diameter, in other words, orthogonal ones are the ones that are furthest apart, then we are done, right? In this set, if the orthogonal ones realize the diameter, then if you have to take a subset of X with smaller diameter, any such subsets, this will imply any subsets of X with smaller diameter cannot have a pair, orthogonal pair. And we've seen in previous application of Borsuk, Frankel-Wilson that the sets with no orthogonal pairs, they are exponentially small. So we are in good shape of an orthogonal pair, which then is exponentially small. So we will be done. Let's look at whether this is the case. All right. So proof. Let's try a little bit. So if you look at again, F is all the half sets, and consider this vector L to be all VF equals to normalize the unit vector 1F minus its complements, the same thing. As in the previous one. Now let's write down their distance and see when they are furthest apart. Their distance is for 2 points, V and W, the little L2 norm expanded, that's the sum of their length minus 2 times their inner products. Okay? But this is unit vectors, so we have this is 1. We have 2 minus 2 times V minus W. This is almost good, except that the inner product of 2 points could be negative. If this is negative, we could go beyond 2. If somehow we know inner product is always non-negative, this will be maximized when they are orthogonal, right? If VW inner product is always non-negative, then we will have this distance maximized for orthogonal pair. And that's exactly what we want. The trick is that to have this property, we don't directly work with the vectors in L, we work with their tensor so that we have this property. So this is second part of the idea. To this end, so we work with tensor. For this, work with tensor. Okay, so let's write down what I mean. For vector v, let's recall, what's this tensor? This just means the rank 1 outer product of a vector. So that just means v transpose, where we should always think of a vector as the column vector. Okay. If you have a column vector times its transpose, which is a row vector, you get a square matrix. And now we're going to treat this rank 1 square matrix as a vector which has n square entries. We're going to treat it as length n square vector in Rn square. So this is the missing part. We will find our set X not in Rn, but in Rn square, so that we have this nice property, and then diameter is realized by orthogonal pairs. So then in this way, for every ij in N, the ij's entry I comma j's entry is vi vj. Right? Now let's consider the inner product, but with respect to tensors. Okay. So we let our sets to be all the tensors where these vectors coming from our original set L. Now, if you look at it, the inner product of two new elements, this is precisely the dot product. The dot product means every entry wise you multiply them. We have n square entries for every ij. The other one, ij's entry is wi wj. This equals to, if you group I together, group j together, that's precisely the inner product of vw twice. So this equals to vw squared, which is non-negative. Good. So by passing to tensor, we do have 2 points are furthest apart when they are orthogonal. So let's double check that. We have, let's compute this guy, but for tensor. It is the same, right? Okay. But look at what is this guy. This is also a unit vector if you take the tensor, because this is just nothing but the inner product with self. We did it above. Just take v equal to w, you get v with itself square, which is its norm to the power 4, right? fourth power, which is again 1, because V itself is a unit vector. So we have this thing equals to 2 minus 2 times the inner product. But the inner product is VW squared, which is always at most 2. All right. Now we just need to realize this is realized by orthogonal pair, and orthogonal pair by our observation here. Use this purple observation. For vectors in L, they are orthogonal if and only if the intersection size is P. Then we can use both Frankel-Wilson. Maybe I should also highlight this, right? Then we get that V is 0 if and only if, let's write it in standard way. Then Frankel-Wilson. Any question? Okay. If there's no question, let's mention one last piece, part of this dimension argument. There's an additional trait. So this additional trick is, our original thing is you have some family which we map to injectively to some vector space, so that they are linearly independent. So we can bound the size of F by the dimension of V, right? And images are linearly independent. The additional trick is that sometimes this dimension is large, which itself is not quite good enough to give a good bound on the cardinality of F, even if we can do this mapping. If we can somehow sneak in, apart from those polynomials or vectors corresponding to F that are linearly independent, if we can sneak in a different set of vectors, another set of vectors, if you sneak in 10 more vectors that are linearly independent to all the vectors corresponding to F, then we can add it to this, right? They are all linearly independent, still less than or equal to the dimension of the vector space. So this new trick is that we add the, let me write it down. Like, if we can add an extra set of polynomials or vectors which together with the original ones corresponding to F, this is corresponding to F, are still linearly independent. Are still linearly independent, then we can improve it. The set of let's say extra x of vectors. Then we have x plus f is at most dimensional v. This is the improvement. Let's see one such example. The example we want to see is but before I mention the example, let me write down a proposition that's useful to use. This is called to verify linearly independence. A useful way to verify linear independence. We've used it implicitly before, but let's write it as a separate lemma, so we don't need to prove it every time. We just need to find some set of points to verify linear independence. This is called triangular criterion. Triangular criterion. The proposition saying that if we have, let f1, f2 to fm be functions in a linear space, if in the vector space, if we have a set of points v1, v2 to vm vectors such that, so what does triangular criterion means? In picture, it just means you have f1 to fm, you evaluate them at m points such that diagonal is non-zero. So this is not equal to 0. But such that diagonal is not 0. So fi, vi is not 0 for every I in M. And half of the triangular criterion, we have fi, vj is 0 for every I bigger than j. So one part of this is 0. Let's see which part. It doesn't matter. This is symmetry, right? So the way I write it, I bigger than j. So it's here, right? The way I write it, this is 0 here. And we don't care about what's going on here. Non-zero on diagonal, 0 here. Then they are linearly independent. Implies f1 to fm, they are linearly independent. Okay. I will not prove this. I'll leave it as exercise. So one example of this new trick to the dimension argument by adding an extra set of polynomials that mutually linearly independent with respect to the original sets is we want to see Katona's intersection theorem. So let's see. Katona intersection theorem. Basically, it's like a mix of Kruskal-Katona and Erdős-Corrado, because we try to minimize the shadow, but we also require the family to be intersecting family. So the theorem by Katona says if we have a family, uniform family, let's say k plus 1 uniform, it's intersecting, then how small can its shadow be? Intersecting means pairwise intersecting. Katona says then its shadow, recall that this is the shadow lives in one layer below, which are all those k sets contained in some elements of F. Then the shadow is at least as large as that of the original family. This is Katona's theorem. It's not hard to see that this is optimal. Try to think of an optimal example. So that's exercise. Find the tight example. How can we prove this? Let's see. Let's try to think a little bit. If we can somehow prove so the hint is that this proof is, I want to say this proof this new proof is by Jing Gao, myself, and Zixiang Xu recently using this new twist. The idea is we find some set of polynomials for the original family, also for the shadow, but actually for the non-shadow, we're going to find polynomials for we're going to find polynomials for shadow for the original family F and the non-shadow. So what is non-shadow? Non-shadow, let me use a symbol, means all the k sets that is not a shadow of F. This is the non-shadow. Okay. Such that they could together degree k polynomial, linearly independent. If we can do this, if we can find this, then what do we have? We have the size of F plus the size of the non-shadow, which is n choose k, minus the shadow, right? This is the non-shadow. Is at most the dimension of the space of all degree and most k polynomials. Okay. What's the dimension of multilinear polynomials, I want to say. The dimension of degree up to k multilinear polynomials are just the number of, this is just the number of degree at most k monomials. Yeah, like x1, x2, this is degree 2, x2, x3, x4, this is degree 3. Because it's multilinear, the power is always 1. So all these monomials correspond to a subset of size at most k, which is the same as number of subsets of size at most k. So that means this degree is the sum of n choose I. You have n variable. I goes from 0 to k. This is almost good. Why almost good? Let's solve this inequality. If you solve it, we get that move non-shadow to one side, cancel the case layer, we will get that f is at most its shadow, but plus the lower layer, and choose I goes from 0 to k minus 1. Okay? Cancel this. So that means to prove our desired inequality, we need to somehow sneak in an additional set of polynomials. Each one corresponds to a set in the lower k levels, correspond to a set of size at most k minus 1, such that together with these two existing families, they are still linearly independent. That will help us to add this term on the left-hand side. We will then finish the proof. Does it make sense? So if we can add an extra set of polynomials linearly independent with the previous two family and corresponds to all sets of size and most k minus 1. So the number of them will be this many. We will be done. That's the idea. So let's write down the these three set of polynomials. F is non-shadow, and this additional sets corresponding to sets of size at most k minus 1. Let's first write the one corresponding to F, the first family. Polynomials corresponding to F. Let's write F as F1, F2 to Fm, which lives in, remember, the k plus 1's layer. Now, we're gonna write, let's write AI to be the short form for the indicator characteristic vector of the I sets in our family, and BI to be the characteristic vector of its complement. Okay. Then we define our polynomial GI of x, where x is a vector, x1 to xm. For every elements in the family, we're going to define the polynomial GI. GI is defined as the products J goes from 1 to K, X inner product with the characteristic vector of the complements Bi minus J. Okay, and then we're going to let Fi be the multilinear reduction of GI. Multilinear reduction, remember, is just that if you have, say, x2 to the 4, x3 to the 5, you all change it to multilinear functions. So first thing to check is that we have obtained a multilinear function for each set in our family. Second of all, we need to check that they all have degree at most k, so that we have this upper bound on the dimension of these low degree multilinear functions, which is true because we have product of k linear terms, so degree at most k. Good. So this is degree of Fi, obviously, is degree of Gi, which is degree of Gi is k. So degree is good. All right. One thing to notice here is that, okay, let's notice later. That's the first family. Now the second family is those corresponding to the non-shadow, but let's introduce at the end. Let's introduce these polynomials corresponding to sets of size at most k minus 1. Actually, let's introduce those first. Polynomials corresponding to non-shadow. What are the non-shadow? All the case layer minus those shadow. Let's also enumerate them as sets T1, T2, TH are the non-shadows. Here, a natural polynomial we can correspond it to, there's a natural one. We can correspond FTI Let's first do the same thing. Write their characteristic vector and the characteristic vector of the complements. So let's write ATI to be the characteristic vector of TI, and then define this multilinear. A natural one is this one. Just multiply of x, multiply the coordinates where this coordinate lies in TI. This is a natural one we're going to use. This is multilinear. Degree, exactly k. It's a k set. You multiply k coordinates. So that's also good. Now the last one, polynomials corresponding to sets of size at most k minus 1. So let's also try to use, let's enumerate them as S1, S2 to SR, where R equals 2, n choose I goes from 0 to k minus 1, right? All the k minus 1. And we enumerate them in such a way that their size is non-decreasing. And for I less than j, Si is at most Sj. Good. After giving them name, we can assign a function. Can let A as I to be the characteristic vector of Si. Here we need an additional trait. We're not just using these, we have to multiply additional factor. Let me write it. So let's first introduce the function GSI of X equals to the product. So the natural choice is you take the product of X, L is in Si. That's the same as this one. But here, we're going to multiply additional factor, which is the size of X inner product with 1 minus K minus 1. This factor is needed later to verify that altogether with the original polynomials, which are the ones corresponding to F, they are still linearly independent. So here, this might not be multilinear because some XL could appear on both. We take FSI, the multilinear reduction of it. Okay. Now we are done with introducing all these three families. The claim is that the polynomials, we have F1 to Fm, those corresponding to F, the first family. And then let's write the last family first, S1 to SR, corresponding to sets of size at most K minus 1. And then FT1 to FTH. This is non-shadow. They are linearly independent. Well, let's see. First, this finishes the proof. If this is linearly independent, as I said, what's the degree here? I forgot to say. The degree of FSI is at most the degree of GSI. This is degree 1. This is degree the size of S. But the size of S is at most K minus 1. So this is degree at most K. We have the whole set being linearly independent. That means F plus R, which is n choose I goes from 0 to K minus 1 plus H. H is the non-shadow, is n choose K minus the shadow, is at most the dimension of multilinear functions. M variates multilinear polynomials. Okay. Then you rearrange the implies what we want. So let's verify that they are linearly independent. We're going to verify using this triangular criterion, meaning we're going to do, let me write it this way. You have by triangle criterion, we have F1 to Fm, Fs1 to Fsr, Ft1 to Fth. The points we're going to verify would be A1 to Am, which are characteristic vectors of the set in our family, and AS1 to ASR, characteristic vector of Si, AT1 to ATH, characteristic vector of these non-shadows. By triangular criterion, we need to verify diagonal term are non-zero. And whenever you take a function, if you feed in an earlier point, it should be zero. That's what we need to verify. Let's do it one by one. Let's first verify that it's true in the first segment. So if you look at what are the definition of this polynomial, I forgot already. Here. So Fi is a multilinear reduction of Gi, and the other two are quite standard. At least this one is standard. That's the third one. The second one is slightly non-standard, which is this one. Good. Let's verify the first one. For the first one, if we plug in, what do we need to verify? Diagonal term is non-zero, right? So we fix an I and verify, evaluate on its corresponding characteristic vector. We have Fi Ai equals to the product, J goes from 1 to K, the inner product of Ai dot Bi minus J. But remember, this is characteristic vector of Fi. This is its complement. That means these two are orthogonal to each other. So Ai dot Bi is 0, meaning that this equals to -1 to the power of K, K factorial, which is non-zero. Good. Diagonal term non-zero. Now we need to verify fix 1, feeding the previous point, it's 0. So let's, we can actually prove even stronger thing. For every two not equal cross term, index not equal, feeding there, it's 0. So we have Fi Aj equals to, write it again, Aj times Bi. minus. Oh, here I also use J, right? That's not good. So let me not write this. But what is this guy? Well, AJ times BI is precisely FJ intersecting the complement of FI, which is the same as, so let me write it. AJ times BI is FI intersecting, FJ intersecting FI complements, which is the same as FJ minus FI. Okay? But what do we know? We know the family F is intersecting, which implies Fj minus Fi. Each one of these set is k plus 1 size, is k plus 1 uniform. So this is strictly smaller than k plus 1 because they share elements. So this is, it takes value from 1 to k. Okay? But if it takes value from 1 to k, then one of these terms must be 0. We get what we want. So we finished verifying the first piece. Let's now move on to verify the second piece. Maybe I'll leave verifying the third one as exercise. The third one is the most easy one. Let's check the second one. So for the second piece, let's first verify the diagonal term is non-zero. Look at FSI, ASI. This is the diagonal term. What does it equal to? Look at here. This is FSI. If you take the multilinear reduction. Well, if you're feeding its characteristic vector, this part just becomes 1. All right? And this part is the size of the set Si. So it's just simply 1 times size of Si minus k minus 1. So equals to size of Si minus k minus 1. But Si is a set of size at most k minus 1. It's less than this. So this is not 0. We need to verify now. Fix everyone here. If you're fitting all the previous one, including these ones, you get 0. Okay, let's first verify these ones. They are easy. For every I less than j, what do we have? We have Si is at most Sj, remember? We order these sets in non-decreasing order in their size, which then implies Sj must have something that Si do not have. This then means FSJ, if we evaluate a later polynomial at the early points Si, ASI, it will be 0. Because, look here, FSJ must multiply everything in the set Sj. But Sj contains something that Si does not have. So in that coordinate, Si corresponding coordinate is 0. So the whole thing becomes 0. That's good. So we can verify this with the earlier point. We just need to verify these points now. This point is where this blue factor comes into play. Now, for every AI, which is the characteristic vector of Fi, let's look at Sj AI. Well, we don't even care about what happened here. Just look at here. This equals to the size of Fi minus k minus 1. The size of Fi is k plus 1. So the blue factor becomes 0. That's why we add it. So the last piece, I will leave it as exercise. Which is ft1 to fth, the triangular criterion. All right, that finishes the proof here. Any question? So today what we did is application of Frankel-Wilson, which is this set with no orthogonal pair and concali is proof of Borsuk's conjecture. And then a new twist of adding additional set of polynomials to be independent with the previous original ones to prove Katona intersection theorem. All right, if there's no question, we will move on to next part on Thursday on Samaridy's regularity lemma. Thanks for your listening and see you guys on Thursday.